Good afternoon to all the participants and other speakers. Uh, so I'm going to deliver a lecture on time series data clustering. Since you have gone through the introduction of time series data uh, sort of analysis, which was delivered by Professor O.P. Vyas and the research scholars. Uh, Certainly, there are a lot of things will be discussed or will be having hands-on on that, which will be done in from starting from tomorrow afternoon to today afternoon. What I'll do is that I'll be focusing on data clustering part, which is related to time series data. So I'll be going quickly to some basics, which I would share with you, and then we'll discuss the clustering part. Okay. So a time series is a sequence of information that attaches a time period of each values. So there are various way of representing the time series or time series data. You can also look at it as set of observations on a quantitative variables collected over time. So time factor is when, like any data you can look for, when the moment you attach a time factor or time stamp to the data, it becomes a time series data for you. So it's a sequence of continuous real valued elements, which is also termed as time series. Okay. So obviously, time series could be analyzed by underlying the structured and function that produce the observations. Okay. Certainly, we can develop mathematical model which can actually explain, or which can actually tell you the steps for prediction, monitoring, and control which may occur in the time series data. Okay. Examples you can have like continuous monitoring of a person heart rate, which is actually time series data. You can have hourly reading of air temperature or daily closing price of a company's stock exchange data is always be a very important time series data for us. Obviously, this methods used in forecasting, there are methods like we may use regression analysis, we may use time series analysis. Uh, you know that in case of regression analysis, what we do is that we are try to find out the relationship between the variables, maybe one or more independent variables, like in contrast for dependent variables. So we are not going in this regression analysis part because that will be covered by Dr. Shantanu Das. What we are looking for is that what is time series analysis, and in time series analysis, what is cluster? How do I go for clustering part? So time series analysis, it's a statistical technique that uses time series data for explaining the past or forecasting future events. That could be like, you know, that prediction is always be a function of time. In this case it could be days, months, years, whatever way you can, based on requirement. Obviously, no causal variables will be required. Examine past behavior of a variable and attempt to predict the future behavior. These are just component. I think you have gone through in the first lecture itself. You talk about time frame, which could be short term, medium term, long term, depending upon like what sort of periods you're looking for. And obviously there you may go for no line of demarcation. That means you may go for any type of time frame also. uh, Trends, which is actually gradual or long term movements up or down of demands, you can consider. Obviously, you can see in the figure that you can always detect the trends out of the graph. Certainly, like cycle is one important thing which comes, because it's what you look for is a repetitive movements of up and down of the demand, which actually creates a cycle out in the particular time series data. So obviously, what you look for is it actually in this case it repeats over a long period of time itself. Okay. Then there are seasonal variations, like based on like different seasons or different events. There are up down repetitive movements are there, which is actually occurring periodically, like often weather related, but could be daily or weekly occurrence could be there. Obviously, we might encounter with random variation also. The this like there is variation which is not easily detectable. So obviously, in this case, it is hard to forecast also, because obviously as far as components like trends, seasonality cycles can always be done accurately, but as far as random variations are concerned, it is very hard to identify. There are some time series terms which we are looking for, like stationary data we look for, which we have already discussed. A time series variables exhibiting no significant upward or downward trends over time, whereas non-stationary means it has significant upward and downward trends. Okay, seasonal data, it exhibits repeating patterns in regular intervals over time. What is actually time series analysis? Obviously, you know that it is very hard. I should not say impossible, but it is very hard to find out the best technique for a particular data set. Okay. Reason is because depending upon like the moment you change the environment, the moment you change the domain of the data, you may be having data of different set of features with different set of attributes with different components as well. So each domain may have a different set of algorithms which could be suitable for that. But analyzing also all such algorithms, all such techniques and methods, that which one is the best out of it is very hard. So what we do is actually we try several different techniques, and obviously what we select is which actually we see that it is working best for my domain. Okay. So what is expected from all of you is that certainly if you are a time series modeler, then you have to keep several time series techniques in your toolbox. So your toolbox must be filled up of such methods which can be applicable. Now come to the main point which I am looking for, that what is data clustering. So clustering is actually a classical data mining, and that divides groups of abstract objects into classes of similar objects. So what we are trying is there's certainly, like even if like you can visualize that certain set of points in two-dimensional data, say xy axis, if you plot some points, the points will be having some sort of regions which have dense points, some sort of regions which have single points or multiple points. So what we do is that we are trying to form a class out of those points, with the view that we will try to maximize the distance between interclass, and we will try to minimize the distance between the points of intraclass. Okay, that is what data clustering talks about. Then what is time series data clustering? So this is certainly is a unsupervised partitioning of data set D into C. C is nothing but it's a set of classes. So we can have n number of classes in such a way that homogeneous time series are grouped together based on a certain similarity measures. That is what we refer as time series data clustering. So what we are trying to do is that we can have n number of classes, we have time series data, then what we look for is based on the characteristics of the data or the properties of the data, or maybe the you can say based on the features of the data, we are actually trying to map the data into different classes. Okay, or we are trying to figure out that what sort of group of data may actually results in class 1, class 2, class 3 and all, because in case of clustering, classes are not known, and data may not be a labeled data. Labeled data, I mean that the data may not be having a class specification. Okay, so we don't have classes, we work on data, and we try to apply some sort of methods, and we try to find out the different classes which might be useful for my domain. Applications, it could be many like aviation, astronomy, biology, climate. You can see that in astronomy, we like pre-processing of outlier detections, say starlight curves, we can have. Biology, we have gene expression, profile alignment, also climate, that climate indices we can work on. We can work on analysis of concentrations at a coastal locations also. Environment and urban, certainly earthquake, regional variability of sea level extremes, or some sort of potential violation of compressive test band relativity is there. So we do for pattern discovery and forecasting in this case. We have finance. Certainly, the forecasting is very much important and useful for finance domain. So we always look for finding out some seasonality patterns out of it. Maybe like in case of we go for retail pattern as well. There are things are there. Obviously, it can be applicable for medicine as well. For example, brain activity. So as far as this time series clustering is there are three types we can look for. This is whole time series clustering, we call it. Then there is subsequence time series clustering. Then there is time point clustering. So whole time series clustering is that clustering is done on individual time series with respect to their similarity measures. Okay. Whereas subsequence clustering, that basically what we do is that we try to actually take subsequence of the time series data, and we try to apply the clustering algorithm on the on that particular segments, which is actually coming from a long time series. Okay. Time point clustering is clustering of time points based on a combination of the temporal proximity of time points and the similarity of the corresponding values. Always remember that this is different from segmentation, because as all points do not need to be assigned to clusters. Okay? Because there are some points which might be detected as noise and could be termed as or referred as noise in this case. Uh, Obviously, uh, then how to represent, what are the representation methods of time series clustering? So we have like data adaptive, then non-data adaptives, then we have model based, and then data dictated. Data adaptive, it actually are performed on all the time series data sets. And what we are trying to do is that we try to minimize the reconstruction error. So, we know that reconstruction error is nothing but it's a distance between the original data points and its projection onto lower dimensional subspace. So it is actually you are talking about distance between the original data points and their estimates. Uh, Very famous algorithms like piecewise polynomial interpolations or piecewise polynomial regulations techniques are there. Now, normally, what we do in PPI is that actually we try to interpolate the given function on each subinterval. Say we consider some subinterval out of the total time interval we have, and then we try to interpolate the given function within that subinterval with a polynomial of low degree. That is what we do it. So this is referred as piecewise polynomial. Uh, Details, if you want, then certainly you can refer the paper. Uh, Whereas piecewise polynomial regression, it is same as what we are doing that we are interpolating the functions where the different interpolating polynomial is used on each interval. So we may go for piecewise linear interpolations and other also. So that is what we do. Then non-data adaptive. Non-data adaptive approaches are representations which are suitable for time series with fixed size, say equal length segmentations. So it is very straightforward when you do comparisons. So that is what non-adaptive does. Model-based is actually the famous models like Markov models or hidden Markov models. These are model-based approaches, which is actually represent a time series in a stochastic way. Uh, Data dictated is actually in contrast, because data dictated approaches like, for For example, the composition ratio is defined automatically based on raw time series such as clipped. Uh, Clipping is a process of transforming a real valued series into a sequence of bits representing whether each data is above or below the average. Okay, that is what. So clip time series requires much less memory to store and can be manipulated faster. So that is what we do it. This is an overview of the clustering algorithms. There are different categories of clustering algorithms available with us. You can see that there are hierarchical methods where actually we have agglomerative algorithms and divisive algorithms. We'll talk about this. Then we have partitioning methods where actually data is partitioned for clustering. So we have algorithms like k-means, Clarence, Clara, and all. Then certainly density-based algorithms also are part of that partitioning methods. So we have density-based connectivity clustering, then density function clustering. Then we have probabilistic clustering as well. As far as clustering algorithm of machine learning, then we have evolutionary methods, then we have ANN and others. And now obviously we are moving forward to have deep learning as well. High dimensional data when you look for, then we have subspace clustering, some projection techniques, then co-clustering techniques available with us. So large set of algorithms available with us. Only what we have to be careful in this case is that as discussion was held during the first lecture itself, that not necessarily that if some algorithm is good or working best for in sort of say non-time series data sort of things, it is not always true that it will work best in case of time series data also. So certainly we have to choose algorithm very wisely. In that case, certainly you have to go through all the properties of the data, and you have to focus on that. What is your requirement out of that, like say clustering or predictions you are looking for? So be careful while choosing the algorithms. Okay, and don't go by the state of art only, where it says that it is workable for non-time series data, then it might be workable for time series data also. So a lot of analysis is required before looking for them. Obviously, the best part is that you go for that you can choose multiple algorithms and you can apply your data on those multiple algorithms. You can compare the results and you can get best out of it. That is what normally the researchers does or do. Okay. Okay. Then a little bit we are focusing, like we just now focus on time series clustering. Then you can see that this particular figure we have taken from one reference. It is referred as 10. This is very, I think, very, what you can see that what the first figure says, it's a raw data based. That means some data comes, you apply algorithm, and obviously you get some clusters or maybe cluster centers. So both way it works for us. Whereas in the second case, the clustering based on feature. So in that case, there is one component added is feature extraction, which you can see that it is added on. First, what you need to do is that you have to extract the features which is required for the clustering. It is not necessary always that all the features which is present in the data could be relevant for the clustering or for could be relevant for any sort of predictions you look for. So what you need to do is that you might be having 100 or maybe 200 or 500 features in some data. Then what you are looking for, that you try to find out the best suitable features which could be used for mining purpose. So there are algorithms for feature extraction also, which is statistical and non-statistical algorithms are available. So applying those algorithms, you can always get relevant features out of it, which could be useful for clustering. The best part in this is that while retrieving this best features out of the available features, it always improve your performance of the prediction or say clustering. Okay. The next is actually the model based, which actually talks about that you could have discretization also, you can have modeling also. In case of modeling, you go for model and you have model parameters, and then you go for clustering. Whereas the other way is that you go for coefficients or residuals to be there, and then we apply the clustering mining methods, and then we get clusters or maybe cluster centers. Just why you can see that why we are mentioning that either we get clusters or either we get cluster centers. Uh, in case of either of this will actually work for you. Say if you get clusters, it is good, and if suppose we get cluster centers out of the method, then those centers will be very important, because from that center point I can actually find out the distance from the points, all the points, and closer will fall in that particular cluster, and rest will fall in other clusters depending upon distance calculations. So that actually helps you to find out the clusters or to find out the prediction. Some preliminary things which actually quickly I'll go through that. When you talk about clustering analysis, then you always go for data matrix. Data matrix is nothing but it's an object by variable structure. It represents n objects with p variables. Obviously, it's a relational table, n by p matrix. You can see that we can represent the entire data matrix in this form, and obviously this matrix will be used to find out the dissimilarity matrix. Uh, Obviously, when you talk about dissimilarity matrix, the object, it becomes object by object structure. Like for example, I can say that I can actually have a matrix where actually all the data points are there in rows and columns as well, and obviously all the elements will tell us the distance between the data points. It could be always remember that it could not be one data points, rather than it's a combination of different data points which actually becomes sample for you. So this distance calculation depends on what type of data you are using. So depending upon that, because multiple attributes may contribute in a single data point. So whenever you talk about distance calculations, these all multiple attributes should participate in distance calculations as well, and that is why we require some sort of spatial data types for clustering analysis, or maybe for the simple analysis as well. Obviously, when you talk about Dij, which you can see the diagonal elements always be zero, because distance between data points from the same data points would be zero. So, what is it is non-negative in nature? It should be non-negative in nature and near zero when objects are highly similar. So that is what we have. So, most of the clustering algorithms operate on dissimilarity matrix. And obviously, if data matrix is given, then you can have always dissimilarity matrix. Obviously, how can we assess dissimilarity? That is what is Dij we look for. So there are things like similarity and dissimilarity you can have uh, with the use of distance calculation. Certainly, you know that when Cauchy distance is there, where actually all xi's are actually the attributes of the sample data. Like you can have I or j 2.2p dimensional data objects you can have. So these all this individual xi1, xi2 is actually representing the individual attributes of the sample, and that will contribute in the distance calculations. So that we can go for. So when we have q equals to 1, you know that this is Manhattan city block distance we look for. And when we have q equals to 2, then we have Euclidean distance, which is very famous and very widely used. One more thing which we can use is weighted distance. Why this weighted distance is important? Certainly, say suppose you have a data sample where actually multiple attributes are there. Like suppose if I say a basketball player data we have, then certainly we may have say the weight of these player, then height of the player, then performance and other things. So there are a lot many attributes could be part of that sample. So what I look for is that I know that, or the domain requirement is that height should be given more weightage while doing the distance calculation. So in that case, what I'll do is that I'll just give a higher weight to height of the player compared to the other attributes. So what will happen is that when distance calculations will be there, then this height will be having a prominent dominance in the distance calculation, and that is what required for the sort of what sort of clustering we go for it. So that is what weighted distance we look for. It can be done like weight can be assigned to the Euclidean distance, because what you do is that just before each of these components, you can see that like xi is minus xj1 is there. Before that, you can assign the weights w1, w2, w3 like that, and depending upon your requirements, you can assign the weight. That is what we have. Data types uh, in clustering, then actually what we have is that we have interval scale variables, then we have binary variables, we have nominal, ordinal, and ratio variables. We have variable of mixed type also. I'm not going in detail for all these. What we mean in this case is that all these variables are actually talking about the variables which are very much present in the data and widely used for prediction and clustering. Interval scale, like as I just told you, that we look for like data type, data like longitude or latitude, or data like weight, height, and all these are interval scale variables. And such variables need to be transformed or need to be standardized so that it can be used for the clustering purpose. Like for example, like it always matters, like always remember that what sort of unit you are using for a particular attribute, it is very much important. Suppose if I am looking for height, then whether I am using centimeter or whether I am using meter or whether I am using feet, that matters for the clustering also. Because the moment you go for lower, smaller units to be used, then certainly the distance will be becomes the gap distance will be becoming big while comparing two different entities. Whereas if I go for higher units to be used, then you can find that you'll realize that the distance between two entities will be uh, less. So depending upon your requirement, you can use higher unit or say smaller units or larger units in that case. Okay. Similarly, we have binary variables where actually, and it's not only binary variables talks about variables of 0, 1 or yes or no. It can actually tackle the variables which is of normal nature as well. Only the thing is, if your requirement says that we require some binary variables to be defined for the clustering purpose, then certainly you can transform even normal variables into binary variables by some transformation methods. We have some Jaccard coefficient for finding out the distance between two binary entities, with the two entities using binary variables as well. Depending upon that, whether it is symmetric and asymmetric in nature, because when you talk about symmetric, that means the when you talk about binary variables having two values, and if I say it's symmetric, that means absence of one will actually lead to the other one. It is symmetric. Asymmetric means it does not. Like absence of one may not lead to the other one. So depending upon asymmetric and symmetric data present in the data, you can go for two different formula we have. We can go for using that. Then we have nominal, ordinal, and ratio variables where actually we look for, like we are having data which has exponential distributions. We have data like where actually ranks could be used. Then we have data where actually we can have logarithmic logarithmic data we have. So there are certain set of data which is of different natures. Then certainly we need to transform such data into required data types, and then we can be used for clustering. And obviously you have the flexibility that out of these all above data types we can make we can mix certain set of data types, and we can have our own mixed data types where actually that can be used for clustering as well. There's one example I can give you, that is standardizing the variables as far as concerned. That what we are doing is that in this case you can find out that what we are calculating the mean absolute deviation. Okay, obviously xi's are n measurements and this mean is m. So what we are trying to find out is mean absolute deviation in this case, and then finding out the z score, which we can be finding out with this formula. The reason behind this mean absolute deviation, because it is robust than standard deviation, because you can always ask that why not standard deviations could be used rather than mean absolute deviation. The thing is that standard deviation, you know that you'll be squaring the terms, so that may lead to some sort of like when you talk about standardizing the measurements, it may not be a proper for you. Whereas in mean absolute deviation will give you some sort of flexibility in that case. So it actually gives you,
Sir,
yeah.
sir, Abhishek asking one question. Sir, which methods to convert the binary variable into normal?
What? Which method?
The
Binary.
Yes, sir. Binary convert the binary variable into a normal.
Binary variable to normal, it is like
Yeah.
binary variable could always be used as normal, because but in that case it will not help you in the analysis. Only the thing is normal data can be transformed into binary variables. Like I can tell you that suppose you are talking about a set of 5 colors, say red, green, blue, white, blue, white, or black, whatever you call it. So suppose your data attribute is having different set of like discrete values are there. Now what you are want to do that you want to transform into binary variables. So I can pick all distinct values out of the attributes and say if I get red, then I can transform this as binary variable as red, and I can assign red not red or red. Similarly, I can assign not green, green, like that. So I can transform some data which is not like in binary, but still I can transform into binary if it is required for your mining purpose. That is what we do. And as far as distance calculation is required for that, certainly we can make use of, as I told you, that we can make use of Jaccard coefficient, which is having the formula. I could have explained it on board, but right now I cannot. But I can pass on the material if required. Okay. Hope this satisfies. Okay.
Yes,
So
sir.
okay, so let me go further. When you apply the method like clustering on certain time series data and all, then we always be interested to finding out the distance between the set of clusters. So obviously, I can define minimum distance, maximum distance, mean distance, and average distance. You can see that what we have, that this minimum distance between clusters Ci and Cj, that could be minimum of that P belongs to Ci, P dash belongs to Cj, and we are looking for P minus P dash. Okay. So what that each of the data points will be compared with other data points of the other clusters, and whatever the minimum distance we are getting, that will be the minimum distance between the clusters. Whereas in maximum distance, we look for maximum distance between 2 points of the two different clusters. That will be referred as maximum distance between the clusters. Similarly, mean and average, that we look for. Okay. Certainly, when you look for this calculation, what we are doing, that it is actually the combination which will appear will be the Cartesian product of the number of data points of one cluster and number of data points of other clusters. So that's why when you look for average distance, the distance will be actually then we look for the 1 by ni nj, which is actually giving you the number of data points which will be generating out of Ci and Cj. Total number of data points, because it's a combination of data points of one cluster to other clusters as well. So it will be a Cartesian product of then I'll just go through a few methods which could be useful for this purpose for time series data clustering, and I'll be giving some like few like introduction to what how in case of larger data set, or you can say in case of big data set, how these algorithms could be parallelized or distributed so that it can be useful for that particular scenario as well. I'll just give some introduction out of it. So I think k-means is the most basic algorithm and it is very useful and popular algorithm. Simple, it works on that for each data points. For each points, put the point in the cluster to whose centroid it is closest. So what you do is that you have data points. Then out of the data points, if you wish to have k number of clusters, so randomly select k-means out of the data points. Randomly you can pick. Even you can pick successive points as well. There's no harm in that. Then what you do
Sir,
is, yeah.
there is another question.
Hmm.
That what is the difference between mean and average distance?
Okay. What is difference between
Mean and average distance.
mean and average distance? Okay, actually what we are doing is that in case of mean distance, we are taking the mean of the individual cluster points of so it's a distance of one mean out of the other mean of the cluster. Whereas in case of average distance, we are take the difference of the point, each points with other all the points of the other clusters we are taking in consideration, and that distance we are taking the average. That is the difference. Okay. Hope it is okay. Fine. See what we are doing. There are cluster, say cluster 1. You have 10 points. You took the mean of 10 points. So we are not looking for Cj in this case. Now Cj, you have 15 points. So mean of the 15 points. So it is actually what you sum the 10 points and by you divide by 10, and in other case sum the 15 points divide by 15. So that gives you Mi and Mj. So when you look for mean distance, it gives you this. Whereas the average distance when you look for, I am just calculating the distance between each point of the one cluster to each point of the other cluster and then taking the average. So that is what the difference between mean distance and average distance. Okay.
There is another question, sir.
Mm-hmm.
How to identify the number of clusters?
How to identify the number of clusters? Certainly, there are few algorithms where actually we specify the number of clusters to be there. Like in case of k-means algorithm, we are specifying that what number of clusters we want. So it is user-defined sort of things, but not necessarily in other clustering algorithms. Other clustering algorithms, naturally, it gives you the number of clusters out of the uh, implementation of the methods. Like if I'll go for the clustering algorithm like density based clustering methods, if you go for, so what it happens is it actually examines each of the points and it examines the distance of the points to all the points, and accordingly thresholding based on the user thresholding of distance as well as minimum points to be in the cluster, we define the clusters out of the whole points. So in that case what will happen is we actually traverse or we actually examine each of the points of the entire data set, and depending upon the constraint of threshold of the minimum distance we are looking for a cluster points, and the number of points we are looking for, minimum number of points looking for the cluster formations, based on two inputs we form the clusters, and it is not definite that the number of clusters will be fixed by you. It can generate arbitrary number of clusters out of it. So there are both ways you can go for. There are certain set of algorithms where you can specify the number of clusters you want, whereas rest of the clustering algorithms, it naturally gives you number of cluster out of it. Like for example, I can tell you that there are algorithms which actually handles the noise also. So in that case, what will happen is the dense points could give you the cluster, whereas there are some compressed points also where actually few points are there which cannot be cluster or cannot be referred as cluster because the participation of the as far as number of points are concerned is very less. So I cannot declare as clusters. So what we do is we actually treat as noise. But when you talk about that where the data is coming like on time intervals, and when you are accumulating data at each time points, then it may be the case that after some time interval there are some points which may be generated or may come in the system which is actually very near to those compressed points. So in that case, there it's up to the analyst to decide that if those compressed points are accumulating, there are accumulating nearby points or having a neighbor points increasing in up to that level, that can be declared as now as cluster. So that also holds for certain set of algorithms. Hope this is okay. Okay.
Hmm.
So I'll be going for k-means. So obviously, I what we do in k-means is this is a sample data set. You can see uh, we have two attributes in the data sample, that A and B. So we have 7 data points. So we have you can see that points are there. What we did is that we have selected two clusters, and randomly we have chosen that 1 and 4 would be my centroid. Okay, so mean will be there. Always remember that in case of k means, it is not necessary that mean will be the data points of the your data set. It could be non-data points of your data set as well. So it is not necessary always. Like we have started with data points, that when you go for the further iteration, you will see that it will generate data points, center points, centroids, which is not part of the data as well. So remember that. So based on these two, then we what we do is that we investigate the distance of the data points to this 1 and 4, and closest will win, and accordingly the clusters 1 and 2 will be formed. Now whatever cluster 1 and 2 you are getting, then what we do is that again take the mean of that, like you calculate the mean of the cluster 1 and cluster 2 depending on the data points which you are getting in this iteration. So obviously in that case you will be generating different data centroids, which you can see that cluster 1 you have 1 2 3, cluster 2 we have this, and your centroid is this and this, and this is not the data points of your data set. So that could happen. And obviously then when you move to this, then you will be having another set of clusters in the next iteration. You will be having 1 2 is falling in one cluster, whereas 3 4 5 6 7 is falling in another cluster. Again you have to find out the centroids, so you're getting this centroids. The stopping criteria is that when you in two successive iterations there is no change in clusters points, then you stop this algorithm, and whatever you are getting the resultant will be the final clusters for you. Uh, Certainly, can you tell me that what sort of disadvantage I can have within this k-means clustering? If I say ask you, the problem with this k-means clustering is that you can see that the k-means clustering always considered all the data points, even if those data points also, which is actually a noise in your data. So k-means has is not having the capability to ignore such noise points. So what it does is that it considers all noisy points also. Say suppose you can see that there are some one point which is far from the other set of data points. So what will happen in that case, that one cluster always be biased towards that noise, because that is higher like compared to the existing data, it is having higher value. So it will actually the mean always bias to the higher value. So the mean will be shifting towards the noise data. So that is the important drawback in k-means clustering. So always remember that while doing k-means clustering, always first remove the noise from the data as far as you can, then apply this k-means. It is very straightforward and it is very effective also. Now this actually figure will tell you that how you can parallelize your k-means. This is actually the instance I have taken from MapReduce sort of implementation of the k-means. As far as MapReduce is concerned, it is actually uh, it's a implementation where actually we can process the things parallelly. What we do in MapReduce is that we can make use of multiple systems. Even we can make use of single system with multiple cores as well, and we can assign the data to the multiple systems or multiple terminals, you can say, and individual terminals can process the data parallelly or execute the methods parallelly, and then intermediate results may be shared to the all the mappers if required, and then finally the final results will be reduced in the reducer component, and finally you get the output of the final clusters. So this is what happening now. What is going on in case of k clusters, k means, sorry. Say there are n number of mappers you have, or you can say n number of systems you have, which is actually a part of your cluster. So you have a big data. So you can actually divide your data into n partition. Not necessarily that partition should be uniform or having same set of data size. It can be a different set of data size also. It can be same also. So what you did is that you have divided your data into different n number of terminals. Now this n number of terminals will actually execute the k-means clustering on the data set which is locally available. So what will happen is randomly you will choose individual mean in case of first mapper, second mapper, and third mapper, and you'll be having it. Then what will happen is that these whatever k-means will actually go for first iteration. It will generate first set of clusters, and data points will be mapped in those clusters. Obviously, all the terminals will generate different data set points for different set of clusters. Now, when you move to the next level of clusters or next level of iteration, then certainly we have to merge the centroids to generate the global centroids. Reason is very simple, because what we are intended here is that whatever individual terminals clusters will be formed, at last we want those clusters to be merged. Like suppose first clusters of the each of the mappers will be merged, then it becomes your global clusters. So merging process requires a uniform centroids to be there. So what actually we are doing in this case is we try to we will what we do is that we merge the centroid, all the centroids we are getting from all the individual terminals, and we find out the one uniform global centroids out of it, and then we are passing to the mappers. Okay, we are passing to the mappers again for the next iteration. So in next iteration, all the mappers are having uniform centroids. Next iteration also, individual will again will give you the different set of centroids, and then again you will be going for global centroid calculations. Then again we'll be back. If in two iterations there is no change for individual terminals, that will be your closing point. And the beauty of that this is that whatever individual terminals have actually formed the clusters, all those clusters are having the same set of global centroids, and then based on the global centroids we can merge n number of clusters into one cluster. That means the first clusters of all the individual terminals will be merged, and similarly second and third and nth number of clusters will be merged, and you'll be getting the global cluster out of it. So this is something which we look for in case of if you have a big data sort of things where actually the data rate is high, volume is high, variety presenting out is present there. That is we look for. As I think we have already discussed this part, it is efficient because it is actually is order of uh, TKN. That means that what is the number of clusters you are looking for, what is the number of points, and what is the number of iterations we are going for it. Okay, so that is what we have. Okay, uh, certainly, as I told you that k-means, or there is a different variation of that is PAM also, partition around radioids, where actually it deals with some noisy points as well, and it is based on PAM is actually based on cost analysis. This is a different algorithm, which is also a partition-based algorithm. Interested one can go. It's very popular algorithm. Uh, the Clara I want to mention here because it is basically built on statistical analysis packages. Okay, so what it does is it actually draws multiple samples of the data set, and then you can apply k-means or PAM. Obviously, if it is noisy data, you cannot go for k-means, go for PAM. If it is noise free, then you can go for k-means as well. The strength of this is that deals with larger data sets compared to k-means or PAM. Okay? The weaknesses is that efficiency always depends on sample size. So what you have is you know the k-means, you know the PAM algorithm. So simply Clara says that you go for multiple samples to be taken out from the whole data and apply these algorithms, and then whatever clusters you are getting, that will serve your purpose. So that is what we do it. Then we have Clarence also, which is actually based on a clustering algorithm based on randomized search. So obviously it draws samples of neighbors dynamically. That in case of Clara, that samples could be actually extracted from any places. Where in Clarence, we look for samples from neighbors, and that actually again the PAM or k-means could be applied on this. Okay. Next, very important, it is very much used in time series data clustering, is hierarchical clustering. Okay. There are two ways of doing hierarchical clustering. Is one is agglomerative nesting, whereas another one is divisive analysis. Uh, just see this figure. Okay, you can see that this PQ RST are individual data points, and then RST form in and like in the first stage RST is having is actually falling in one cluster, whereas PQ is falling in another cluster. Then RST further can be divided or partitioned into S and T and then R, and then at last you'll be getting PQRST. So all the data points on top is in one cluster, whereas in bottom all individual data points form a cluster. And in the intermediate nodes, you can see that they are actually forming clusters by merging individual data points depending upon distance calculations. So what we do in this case is that if you go from bottom to top, so bottom up approach which you, it is agglomerative. That means you are what you are assuming that individual data points is my cluster. So if you have n points in your data, you have n clusters in your data for this agglomerative point, and then you move forward upward and you get all the points form a single clusters. How to get the clusters which is for you, that you can always draw a line somewhere in the label. So if I draw a line just in after the root of this particular tree structure, then if I draw a line in the first label itself, then I'll be getting two clusters, say PQ and RST. Whereas if I'll draw in the next line, then I'll be getting PQ as one cluster, whereas ST is one cluster and R is another clusters. If I go again below the line, below the label, then I'll be getting individual data points in the as in clusters. So where what number of clusters you want, it depends on where you draw a line, then where in what level you are drawing the line, and all intersection point will give you individual clusters for you, and obviously all the data points which is falling in that branch, so that will be the cluster points. There are hierarchical algorithms which is single link, MST link, then minimum spanning tree, then complete link and average link. This is widely used. This is what the concept which comes in hierarchical uh, clustering algorithm. We make use of dendrograms. This particular figure is referred as dendrograms. What we do, you can see that just I told you that you can draw a line. So if you draw a line at the lowest level, then individual data points will be clusters. If you go one above, then you will be having one, two, three, four clusters. If you go above, then you will be having one, two, three clusters. If you go above, then you will be having two clusters. If you go above, then all the points will form one cluster itself. So depending upon the line of intersections which you draw, the number of clusters you will retrieve. That is what we do it. Okay. So this particular figures we actually generate out of the clustering, and the clusters could be retrieved by drawing the line at any level of the this dendrogram depending upon your requirement. So this is single link. How this single link is actually, it works on cluster similarity, that similarity of two most similar members we look for. So this is what we have a dissimilarity matrix we can have out of your data point. Say in my case it is 5 points, so we have dissimilarity matrix out of it. Then we look for minimum points to be there. So you can see that 2 is the minimum in this particular dissimilarity matrix, and it refers to 1 2. So what we do is that we merge the 1 2 in and formed one cluster. So you can find out that we have started the dendrogram as 1 2, and we are joining 1 2 together. So and now the question is that when you move to the next matrix, then obviously two columns must be merged, because now 1 2 becomes one cluster for me. So the merging criteria, you can see that we are looking for minimum out of the distance which we have in 1 2. So it is minimum of distance of D13 and D23, and it will be 6 3 and it will be 3. So you can see that 3 is now the data points in the matrix in the next iteration. Similarly, you can have other calculations. So you can have another matrix. Now investigate this matrix, find out the minimum one. So again, you will be getting the 3 as minimum one. So that you can go for. So 1, 2, and 3 now will be merged. So you can see that the dendrograms I am going for is this. Similarly, the same set of things will be there. Minimum of the two columns will be the part or data points of the improved matrix. Similarly, this. So this is what you get out of the final one. So this dendrogram is actually you can form, and you can see that it actually reflects different set of clusters could be formed at different levels. So based on your requirements, you can retrieve the cluster out of it. So similarly, in case of complete link, in case of single link, what we have, that we have considered the minimum distance of the columns, whereas in case of complete link, we are talking about maximum distance will be considered for the improved matrix data points. So this is what we do. Like you can see that out of 6 3, 6 is maximum, so 6 becomes the data points of the improved matrix. So similarly, we can do that, and we can have window diagrams like this. Again, clusters can be retrieved. Similarly, average link, you can say that instead of going for minimum and maximum will be considered as data points for the input matrix, what we do is that we take the average of both the points. So you can see that what we are doing, the 6 plus 3 by 2, it is 4.5, so it becomes that. And again, investigate the minimum one, you will find that the dendrogram creation will have different set of you can say sequence, which was in complete link and single link, though it forms the same set of cluster out of it. So this way you can have the dendrograms and clusters out of it.
Sir,
Yeah,
there is a one query about the single link. Can you
yeah,
explain the again?
okay. So this is single link. See, this is the data matrix. Say suppose you have 1 lakh data, then suddenly the matrix will be of 1 lakh data by 1 lakh data only. So you have to deal with that. So I'm just considering the 5-point data, and I'm considering by some sort of distance calculations, I have calculated the distance out of it. Okay, so this is dissimilarity. So this shows individual data point shows the distance between 2 points. Say distance between 1 and 2 is 2, whereas distance between 1 and 3 is 6. Okay. So upper triangular matrix we have not considered because that is same as lower triangular matrix. So this now how to deal with the single link. See, investigate this matrix, just find out the smallest data points, smallest difference. So this is what 2 is the smallest one. So we consider the first case 2, 2 corresponds to 1 and 2. So now the first cluster will be formed, or you can say temporary cluster will be 1 and 2. Now, when you go for the improved matrix, then this 1, 2 becomes 1. That means one column. So what you have is you have two different columns of 1 and 2. You have to merge these two columns as one. So merging criteria says that in case of single link, I'll be considering the minimum of 6 and 3, 10 and 9, and 9 and 8. So minimum of 6, 3 is 3, whereas 10 and 9 is 9, whereas 9 and 8 is 8. So this becomes your data points. Now investigate again this matrix, find out the minimum one. So 3 is minimum one. So next will be this, and the same set of steps will be followed for the all future steps. So you'll be then you'll be getting this part, and your clustering will be over. Is that okay? Okay. So so this way you can apply this complete single and average link. Uh, there is one problem with dendrogram, that when you have large data set points, then whatever dendrograms you are getting is messy. So it is very hard to detect the clusters out of it. So that you have to look into the matter. Certainly, it is better always go for parallelizing the entire process. Uh, when you look for clustering large data, then we have algorithms like balanced iterative reduced clustering hierarchy, which then DB scan, which is uh, uh, density based clustering using having with noise, whereas Cure is having clustering with representatives. So all these algorithms are very much useful for large data. And it is, let me tell you that DB scan and Cure is widely used in time series data clustering also. I'll give you that the which, as I told you, that balance attribute reduced and clustering using hierarchies, whereas Cure clustering using representatives. So I'll be giving some sort of details of this birch and Cure also, and then we'll move to DB scan.
So, will we have any hands-on session on TB scan or Cure or Birch?
Okay, certainly, I'll just go through it. Probably Dr. Santanu may not. Like if time permits, certainly we can go for it. So I'll try. If you are like, if you all participants are ready to do
Okay.
that, then certainly we can do that. Hmm. Because certainly in that case you have to devote more time.
All right.
Like we can do it in say after 6 or something like that. Is that okay?
Oh, okay.
Okay.
Okay, sir.
Okay.
Thank you, sir.
So balanced iterative reduced clustering hierarchy, it is incremental in nature, it is hierarchical, and the best part is it is one scan. One scan means that means when you are reading the data out of your memory, or you say disk, it is just one time reading would enough for this particular method. Okay. So clustering features used in this case is what we call it as CF. It actually N, LS, and SS. N is number of points in clusters, whereas LS is sum of points in the clusters, whereas SS is sum of squares of points in the clusters. Okay. So CF tree is actually a balanced search tree. Nodes has CF triplets for each child. Leaf node represent clusters and has CF value for each subcluster in it. Subcluster has maximum diameter in this case. So obviously we fix up some sort of thresholding also. Thresholding in the case, this is what sort of a snapshot of one uh, birch clustering outcome. Uh, you have roots, then you have several branches. You can see each of the nodes are having a set of clustering features. just take the first one. See, CF1 is having child one, then this child one is having again, there is another this is child. So again, this child is having different set of clustering features. Then each child is having another branch, and there are certain branch which have siblings as well. So, and obviously, at last, what you are getting, if this is a leaf, then these points will fall in that particular, what do you call it as clusters. So what we have is that just see that this the below one is a cluster. So what we have is that out of these points, this CF1 is calculated, and this CF1 will actually be the responsible for calculating the CF of the parents. What is that is that we find out the cumulative CFs of CF1, CF2 to CF6 to calculate the CF of this child one, which is the first part. And then all these CF, which is which is actually CF1, CF2, CF3, and CF5, this will actually generate the CF for the root, which is of child one. So that way it works. Okay. Uh, what it does is that actually, if you look on that at the level of leaf, you can apply any simple algorithm which could actually generate clusters for you, and then you start designing this tree, which is balanced in nature. What if, like, the question is, it may be the case that you have certain set of data, you have actually generated this particular tree. Now the question is, if new data comes, what will happen? Okay. Now, obviously, if new sample comes, certainly you will investigate that new sample. Where we can put this new sample? So obviously, in that case, we'll actually compare the distance of that new sample to the existing clusters, and it may be the case that it may fall in the first cluster itself. But if you see that all the blocks, like say CF1 to CF6, is full, but still there is a possibility that that particular sample is actually closer than CF6, say the point which is actually referring CF6, uh, then in that case we have to make a space for that particular point. So in that case, what happens actually, we actually insert the point in the desired cluster, and if required, the extreme points can shift to the sibling. And similarly, if the next sibling also is full, then the again extreme points will move to the next sibling also. And in case suppose your sibling threshold is over and still one point is not actually falling in that cluster, in that case, that point will actually fall in different clusters based on the distance, because now, depending upon the criteria of the distance calculation, that points will fall in other clusters as well. Or if you have if you have space available or block available, you can fix up that point in that. So this way we move off for this particular CF tree. So insertion, and even if you want to delete some points also, you can do that also. So whenever you do this, obviously you'll realize that the moment I change the data points in the clusters, this CF will change, because this CF depends on the data points. Obviously, it may be the case the number of data points are not changing, but the data point is not changed. So that data points, because what we have in clustering feature is sum of the data points in the clusters and the sum of the squares of the points in the cluster. So that you have to recalculate, and this recalculation will go back to up to the root, because if we recalculate this CF1, then we go for intermediate node where actually the CF1 is recalculated, then again we go back to root where CF1 is recalculated. So that sort of manipulation is involved. This is minor manipulations, and it can be done through programming very easily. Okay, so this is what Birch states that, and obviously all leaf will actually tell you the clusters, final clusters out of it. And it is dynamic and incremental in a way that there is no need to re-execute the method or re-execute the algorithms. Rather, it can accommodate new points by inserting at a proper place. That is what the beauty of this algorithm. Obviously, it scales linearly. It's a one scan process, and complexity is order of n only, as many numbers you have. Only the thing is that it handles only numeric data. So, and obviously, it is applicable for time series data because normally in time series data, we have numeric data, and there are some categorical data also which can be transformed into numeric data as well. So that is what it is useful in that case. Next point, next is cure, which is clustering using representatives. It uses many points to represent a cluster instead of only one. For example, you can see this particular figure. This is your sample of data. Now you have three clusters, you got it by representative points. These black points are representative of the clusters. So first cluster we have two representatives. Then again the next cluster below that is two representatives. Then there is two representatives of the third clusters as well. Now, out of this, the cure actually what it does is that it actually shifts the representative points also. So it is what we call it as shrink representative points, and we merge also clustering points. What we do is in this case that you can see that one representatives of the first cluster and another representatives of another clusters. If you look on the distance between these two representative points, then we found that this is in our within the threshold of within the minimum distance criteria which we have fixed for the points to be in one cluster. So in that case what we do is that these two can be merged as one clusters, and now these two representative points becomes your representative points, where these 2 points becomes your data points for the merge clusters. Now these 2 points may not be a part of your cluster data set, or may be a part of the database set as well. So it is not necessary that these two representative points could always be a part of your data set. When you shrink the data representatives, so what will happen is this particular data points which is representative of these clusters may shrink to, and it will go to the denser points, near to the denser points. So that is what we call it, sinking of the representative points. And this is very effective for the clustering purposes. So obviously shrinking could be done towards the gravity center by a fraction of alpha, and obviously alpha will be defined by the user itself. As far as algorithm, it is very simple. Obtain a sample of the database, partition the sample into p partitions, partially cluster the points in each partition, then remove outliers based on the size of clusters. Obviously, completely cluster all data points in sample, and cluster entire database on disk using C points to represent each clusters. In an item in the database is placed in the cluster which has the closest representative points to it. So it is very simple to implement. As far as effectiveness, it is order of one scan only. Complexity is again order of n, depending upon the number of points. Obviously, it is sensitive to user-defined parameters. Obviously, you are defining the sample size, you are defining the desired clusters you look for, and obviously, you are defining the shrinking factor. So, you wisely, if you do that, then it is very effective in nature. Obviously, it cannot handle categorical data also. Then at last we'll be looking for density-based clustering methods, where actually there are so many methods which is in place, starting from dbscan, then optics, then clue and click. Certainly, uh, the best part of it, this particular clustering method is that it discovers clusters of arbitrary shape, and it has the capability of handling the noise as well. And in most of the cases, it is one scan, and obviously need density parameters as termination conditions. So dbscan stands for density based spatial clustering of applications with noise. So it is actually handles the noise also. There are two input parameters which is defined by user. That means you people, if you are going for the analysis or clustering, then you will decide the minimum points, and this epsilon is actually the radius what we look for. So minimum points means what you define is that if one point, and if suppose you decide the closeness of the points in terms of distance, then within that distance radius, if number of points matches with this minimum points, that means it is either the same or greater than, that could be referred as first tentative clusters of out of the data points. So there are some basic things which actually leads to the this particular clustering. You can see that a distance measure is defined on dB, and the distance between any PQ is denoted by distance PQ. The first thing which we will define is the epsilon neighborhood of P, denoted by epsilon NBHD. P is a subset of database or data set, whatever you call it, such that distance PQ is epsilon for any Q belongs to epsilon neighborhood of P. So what we are trying to do is that, say you have n data points, you can randomly choose one data points to start. So choose the first point, say any point you can choose it. Now consider the epsilon distance, whatever you have fixed. So epsilon distance, draw a circle. Now within this circle, whatever points falling inside that will be referred as epsilon neighborhood of P. So that is what we were defining in the second point. We define core point if the number of points within the epsilon neighborhood of P is greater than or equals to minimum points. So what I am saying is, suppose I am saying that, okay, 5 is my minimum points. So if epsilon neighborhood of P is having more than 5 or equal to 5 points, then I can declare P as core points, or you can say the first level of clusters. Now we investigate the boundary points also, because we are looking for another set of points which may be the part of the cluster. So then we investigate the boundary points. Then we have the basics like density reachability, then density reachable and all. So given PQ, which is belonging to data set, if Q belongs to epsilon neighborhood of P and P is a core point, then we say that Q is directly density reachable from P. Now, if Q is density reachable from P, if there is a sequence of points P1, P2, and Pn, okay, such that P is P1 and Q is Pn, and each point Pi plus 1 is directly reachable from Pi, then Q is directly reachable to P. That means in this case, you can see, if you look on the figure, there is B2 and there is B1. You can start from any point. Say you have started your method with B1. So you got minimum points criteria and then go. So what we got is that B1 is accessible or density reachable to A3, A3 is density reachable to A4, then A1, then A0, then A2, then A5, then B2. So from B1, B2, you reach, that means B1 and B2 will be the part of the same cluster by the virtue of density reachable, because all these points are densely reachable to each other. So that is what we explain here. And this dotted line, which is small dotted lines you look for, this arbitrary shape when you look for, this whole shape will actually be the one cluster out of your data. And obviously, once there is no such points we find, then you move to those points which are not assigned to the clusters and randomly pick another points, and further you go for the same set of iterations, and you will be going for next set of clusters. Similarly, this process will go on till you exhaust all the points. This is what we do in DBScan. Similarly, you can see that by figure epsilon neighborhood points. Say if you see a minimum point is 4, then we go for this epsilon neighborhood. I can fix up anything, like I can distance calculations. If unit is there, I can say 2 centimeter, I can say 2 meter, 2 feet, or anything, whatever distance units you have used, or that unit can be used here as epsilon distance. And if it is P, can be referred as core point if then minimum point criteria is met. And obviously Q and R is density reachable, because R is reachable to this middle points and middle point is reachable to Q, so Q and R is density reachable. This is what we have. Obviously, I already told you, you can start with arbitrary set of points, arbitrary selector points, retrieve all point density reachable. Then P is a core point, a cluster is formed, so it is a elementary or first level of clusters. And then by virtue of density reachable concept, we can form arbitrary set of clusters. Obviously, DV scan works on order of n square because we are actually investigating the points uh, by n square sort of n squared sort of terms. Whereas if you use partial index in this case, then this particular uh, complexity could be n log n as well. So it is actually sensitive to user defined parameters. This is what we have is a map reduced DB scan. This particular figure says that how the DB scan can be used using map reduce framework in terms of processing the big data or say huge data you look for. So it is the same sort of system as we have defined in case of k-means, that multiple terminals could be part of your entire process, and obviously each terminals will get some set of data, and it will actually execute the algorithms, and individually it may form the clusters, and those clusters is supposed to be reduced to a global clusters, and then finally you'll get the output. Now in this case, we are assuming that there are two terminals having two individual local data. They have applied DB-scan algorithms. They have their own set of clusters. Now the question comes that we have set of clusters from say terminal 1. Now we have another set of clusters from terminal 2. Then how to merge or how to get the global cluster out of these two terminals? Then this particular figure will explain that part. What we are doing in this case is the left part is actually a one cluster from getting from one terminal, and right part is a cluster which we are getting from another terminal. So I'm just so we have two different clusters. What we do is that we are defining the outer region is OR of S1, whereas inner region IR of S1, and this is S1 and S2 is actually your clusters from two terminals. Now we are just what we are trying to find out is we are trying to find out how to merge and to get some sort of clue on virtue of which I can merge these two clusters. So what we do is that where this like these two clusters might share some sort of boundary. It can be at any directions. It doesn't matter. Certainly, we have to investigate all the directions also, all the points. So what we are looking for is that you can see that uh, the the region of the outer region and inner region, if when you draw, it is actually of epsilon distance. So S1 is the bold line is your S1 and S2. The big dotted line, the small dotted lines are actually outer region. The big dotted line, big dash lines are actually inner region. This distance between this particular bold lines with inner region is epsilon, and obviously the outer region is also epsilon. So what we are trying to find out is the epsilon distance points we are trying to find out. So what will happen that this is my boundary, which is actually shared by S1 and S2. It could not be that the same boundary, it could be of some distance as well. What we are trying to find out is, let us take a point, red points as px, go for epsilon distance, and then draw a circle of radius epsilon. Then there may be a case that this particular circle may have certain set of points from S2 and certain set of points from S1. If that particular condition holds, then by virtue of density reachable points, I can merge these two clusters as one global clusters and will be referred as your final clusters out of it. So this particular investigations should be done on all the clusters of all the terminals, or that combinations could be Cartesian product of the number of clusters of one terminal to the another terminal. And you have to investigate that, and you have to merge those clusters to get the global. So I'm just going to the last part of my talk. These are some clustering evaluation measures where actually you can make use of purities, then We have Rand index, then F measures, then entropy, then we have Jacquard, SSE, and all. So I'm just going like we. I think we are going beyond our time limit. So purity can be defined in some sort of mathematical term. Then Rand index can be defined in terms of true positive plus true negative, then true positive plus positive, false negative, and true negative also. So, so there are a set of formulas which you can F measures could be defined in terms of precision and recall. Normalized mutual informations could be defined as this formula where actually Y is class label, C is cluster labels, H is entropy, whereas I is in mutual informations. That is information content of Y and C. Entropy, you know that this entropy is very much useful because it is also used in classifications like all type of decision tree methods. We make use of this entropy also. ID3 algorithm make use of this entropy. So entropy of a cluster shows how dispersed classes are with a cluster. So this should be low always. So this is what we have. PI stands for, that means a probability that a particular data points falls in particular class CI. So that is the probability. So similarly, Jacquard score, then internal index will be used for your as measures. Obviously, as far as four aspect of studying time series clustering, then we have, you can see that we have dimensional reductions of time series, where actually a lot of algorithms we use, clustering algorithms, then some sort of prototypes also. Then we have similarity measures between time series. It can be Euclidean or others also. Just last slide, which I just want to do that uh, uh, time series are essentially high dimensional data, whereas mining high dimensional involves addressing a range of challenges. The first is the curse of dimensionality. I think all of us are obviously the meaningful one of the similarity measures in the high dimensional space is very important. What actually curse of dimensionality actually states that when you go for a higher dimension of the data, then your data point, the distance between the data points becomes sparse. So in that case, actually the cluster formations sometimes becomes inefficient also. So you have to be careful while doing such sort of you can say analysis where actually high dimensions are actually involved. So there are ways of considering the high dimensional data into lower dimension also. That means you can transform the higher dimension to lower dimension also, and you can have the methods to be used. But be careful of regarding this also. So obviously, what we have the important task to enhance performance on time series is the reduction of the dimensionality that must preserve the main characteristics and reflects the originality. It may be similarity or dissimilarity of such data. This is sometimes referred as lower bounding. Okay. This is some sort of packages of time series clustering is actually done by some of the researchers. So TS clust, this is all actually, and there is DTW clust. So time series clustering along with optimization for the dynamic time warping distance. So this link is available. You can go through it. Algorithm of time series clusterings based on connectivity based clustering, hierarchical clusterings. This paper is where you can go through this paper. Then centroid based clustering, you can go this paper. Then distribution based clustering, you can go for this paper. And there are so many papers you can have. There are so many surveys that has been done. There is very one important survey done in 2000, way back in 2005 or 2007. It's very, you can go through it. Even one survey which is done in 2018 also on time series data clustering. It is very, you can go through it. That will help you to do that. There are some references which actually from which I have used the contents.